Okay, in this video we're going to be going through the process of doing a nested DC transfer analysis in Xschem and Ngspice, and we're going to look at various options for doing that and how to get the data out of Ngspice into a format where we can import it into a variety of different tools for further analysis beyond just simply plotting the data. We're going to use our current mirror diff amp as a demonstration vehicle, and we're going to be, at this point, just simulating some voltage transfer characteristics from the non-inverting input to the inverting input, or rather to the output for different values of the inverting input. And so the first thing to do is to fire up Xschem and take a look at how I've changed the transistor level schematic and made a symbol for it in order to put it in a test harness and do some simulations on it. So let's look at the schematic. And mainly what I've done since the last video was to replace the net labels here with pin labels. And I've also replaced the VDD and ground power flags with pin labels and changed those to VP and VN in preparation to put this into a subcircuit wrapper, and these will be the pin labels on our subcircuit, and they'll be corresponding pin ports on our symbol. Okay, so that's how I've changed the schematic. And now let me open the symbol that I've created. So that would be this one. And so I've made a symbol that looks sort of like an op amp here with power and ground terminals. And I've also put an extra terminal down here for the bias input. So this would be VB. This would be, we could either apply a voltage here if we wanted to, or we could sync a current from this because we put the diode connected transistor to form a current mirror in with the bias transistor. So we're going to be driving it with a current in this particular case. But you can see that I've made the names here correspond to the pin labels. So there's V1, there's V2. I think the third one I made was the out, and then that's my line. This is VB, that's VP, and that's VN. And then I've put the global property for this this particular symbol. I've made the type equal to subcircuit, and here's the format. The format is just the name of the instance, the pin list, which should come out in the order of creation of these symbols, and the symbol name, which would be the CM diff amp, which would correspond to the name of the subcircuit, and then the template property. So this says that the default name is going to be X1, but if there's already an X1, it will change the number to make it a unique instance identifier. So that is the symbol, and now we're going to open the test harness that I've created. And so that's CM diff amp underscore VTC. I've instanced one of my CM diff amp symbols, and if I select it and hit the E key, I descend into the transistor level schematic of that, so we know it's hooked up to it, and then can go back up. I've connected the power rails up to VDD and ground, and I've got my VDD voltage source over here. I've got my input voltage source, which in this case is just a DC source, and I've got a reference voltage source hooked up to the inverting input, and I've got a current source pulling 1 microamp out of the VB input to the amplifier. I put a 2 picofarad load on the output. Obviously that's not going to make a difference for the DC transfer characteristics, but eventually I'm going to do some AC simulations here, so I'm going to put a 2 picofarad load on the output, and then I've got my models, my typical models, and now I've got my little Spice directive here that says I want to do a DC transfer analysis sweeping V in from one rail to the other in 1 millivolt steps. And instead of saving everything, I've decided to save just V out, the voltage on node V out, the voltage on V ref, and the voltage on V in. And I found when I saved everything, given all the transistors and all of the parameters in all of the transistors, that it was creating in a very, very large raw file when I did the simulation, almost to the extent where it took, I think, 3 gigabytes for the raw file. So I decided not to save everything for this particular analysis, but just the nodes I would be interested in plotting. Okay, so I'm going to do what we've been doing before, and that is a netlist, and then simulate. And I've discovered in the process of preparing for making this video that most of the time that it takes to do the simulations actually seems to be in parsing the models from the PDK. These models are so large and include so many parameters and so many variations that it just takes a long time to read in the model files. Actually taking the time it takes to actually do the simulation, which we'll see in a little bit, is actually quite small in comparison. So we'll dismiss that now that it's done, and we'll pull up GAW. Okay, and select the panel, and let's plot V out. There's our voltage transfer characteristic, and just to show you where V ref is, there's V ref at 0.5 volt. And there's the identity line, V out versus V in, and we can see that where the green line crosses the red line roughly coincides with where our high gain region is centered. So this is precisely what we would expect for a circuit like this. Okay, so that's all well and good. I still to this day do not know how to get the data out of GAW and into something like a CSV file or something like that. I know it lives in the raw file, and I should be able to find a way of parsing the raw file directly. There's probably some kind of Python library that does that. But as for like exporting data from this, I haven't seen a way to do that yet. Okay, so let's go back and try to do a nested DC sweep. Okay, so in Ngspice, we can sweep. In the DC transfer analysis, we can specify we want to sweep 2 sources or even more sources, and we can do that by just saying, here's listing a secondary source here, Vref, and we want to sweep that, let's say, from 0.25 to, oh, I don't know, maybe 0.75 in 0.25 volt increments, so that'll give us 3 different values of Vref at 0.25, 0.5, and 0.75. And that's a little bit off the screen, so let's save that. Let's netlist and then simulate. And then we'll go to GAW, and we'll try to do the same thing. Okay, so we're going to select this pane. We're going to do via vout, via vref, via vin. Well, that's kind of strange. So we'd like to see 3 different voltage transfer characteristics. Maybe one here, and I don't know, one somewhere in the middle here. But instead, what we find is this kind of weird thing going on where we're here at 2.25 on vref, and then we make a step change up to the final value of vref, and we only get one of the output voltage transfer characteristics. So there's something weird going on here. GAW doesn't seem to know how to deal with these sort of nested DC sweeps. I believe what happens in the raw file is that the results of the simulations are just concatenated together so that you just get a big long vector, and I think GAW just thinks of it as one sweep or something like that. But I still don't understand kind of where the middle value of vref is here. Because we had 3 different values, and we're just kind of getting the beginning and the end here. So that's kind of a mystery. And so this is not a very desirable way of doing things, both from the standpoint of it not dealing with the nested sweep properly, and also it not giving us an easy way to export the data, at least that I've been able to see. So what are we going to do? Well, what I'm going to suggest is that we change the simulation tool configuration here, and we, instead of using the batch mode, we use this mode here, which is going to open up a terminal window. It's going to launch Ngspice in terminal, and it's going to drop us into the Ngspice prompt after we're done. And so we're going to save this configuration and close down this window. And so now we're going to netlist and simulate. And so we get this window popping up here, this Xterm, and we see the same sort of message that we would have gotten in the dialog, which is what Ngspice had produced as output when it ran. And after it's done running, it will drop us out into a prompt, which is the Ngspice interactive interpreter. And so actually you just saw the whole thing. That was the simulation. That was the entire simulation of the 3 DC transfer curves. When that stuff appeared on the screen, it took like 2 seconds. All of the rest of that was that time delay was the parsing of the input model file. So now if I go, I can go plot V of V out. And here is a plot of my 3 DC transfer curves. One corresponding to the 0.25, the 0.5, and the 0.75. And if I like, I can plot more than one curve. I could plot V of V out, V of V ref, and V of V in. And you can see here the same type of plot that I was doing before, where you can see where vref crosses the identity line, and you can see that that very nicely corresponds to where the high gain region is. So that we can plot the data using this. If we wanted to write the simulation results out, we can do that using a command which is called, I think it's WR. Let me just pull it up just to, actually I think I downloaded a copy of the manual. Just let me, so the Ngspice 34 manual gives us, so chapter 17 is the commands in the interactive interpreter and the scripting languages, and so the command I'm interested in here is WR data. 17.7 is all the commands, so let's see. Yeah, WR data. And I'm going to set the WR single scale variable and the WR vec names variable. That's what I wanted to look up. So if we do set WR underscore single scale, that's sort of the variable that's being swept, and we only want that column repeated once. And we set WR vec names. This will print column headings. And then we can do WR data, and let's call this cm diffamp vtc.txt. And let us put out v of vref and v of vout. And now that winds up going into the directory where all of the netlists are. And so that's .xschem simulations. And there, let's see, cm diffamp vtc text. Let's see, gvim. And so here, it's not a tab delimited text file, unfortunately. It's a, these are spaces. So it's written the data out for us in a tabular format with fixed column widths. But there's the data. And so this is the value that's being swept, which is v in. This is the value of vref. This is the value of vout. Just as we specified, the columns come out in the order that we specify them. And you can, if we page down here a ways, you'll note that these are just concatenated together. So here's the value of vref being 0.25, and when we get down to line 1802, I think, there are 1,801 data points, and then one for the title row, we switch back to 0 on vin, and then we switch to the new value of vref. And so the three simulations are basically just concatenated together here. So you can work with this file in a number of different ways. If you need to have I don't know if like MATLAB will import this kind of file directly from the import data wizard. One option would be to do a search and replace on the spaces and make them commas to make it a CSV file. Another option that is pretty easy on Linux with LibreOffice installed would be to, let's see, I'm showing hidden files so I can see my Xschem directory. So if I go into .xschem simulations, there it is, and I right click on this and I open it with LibreOffice Calc. I can say I want, by default, this is how the thing comes up, and it doesn't treat spaces as a separator. So if I switch to spaces as a separator, it will quite nicely, and you merge delimiters and trim spaces and things like that. You can get this very nicely to be imported into LibreOffice as a spreadsheet. And then, of course, you can get rid of this column, which probably comes from some leading spaces. So if we delete, let's see, edit, let's see, format. See how often I use LibreOffice Calc. Delete columns, how about that? All right, so what we could do then is just, we could change these also here at this point if we wanted to say that this is vin, vref, and vout, just to make it the names cleaner. We could export this as a CSV file, save it as a CSV file, edit the filter settings, save, and we could, let's say, take out the quotes for text delimiters, and let's see if there's our CSV file. If we open that up with gvim, there's our CSV file. So it's fairly easy to convert that into a CSV file through reading it into LibreOffice, and that might be a more useful format for working with the data in, let's say, MATLAB or something like that. So that's one option that I wanted to show you. So let's exit from that, and let me put this away for the time being. And let's go back here. So that's one option. Another option would be to use a control block, and I wanted to introduce that notion. Let's see if I can remember how to do this. So if we go .control, this allows us to embed some of Ngspice's interactive interpreter commands into a little script or something that will run after the circuit's been parsed. And so we can, this goes in between a .control and .endc, and if we do DC vn 0 1.8 0.001 vref 0.25 0.75 0.25, and then we type run, and we can do plot v of vout, v of vref, and v of vin. So I've commented out this DC transfer analysis, and I've commented out this save, and I've replaced them with these commands for the interactive interpreter inside this control block. And so you put a star in front of a line in the first column, that makes it a comment as far as Spice netlists are concerned. So let's give this a try. I'm going to save this. Renetlist, simulate. And there you can see that it's run our little script here. And it's made the plot for us. So here's the 3 voltage transfer curves in a similar way to we had before, interactively. And the data here we can also save. So it's dropped us into the interactive interpreter, and if I go display, it shows me all of the vectors that I can do something with here. So it actually did save all, and that apparently worked okay. But I can, for instance, if I wanted to plot the common source node of the diff pair and see how that's behaving here, I happen to have looked that up. That happens to be net1 of subcircuit instance x1, and that's x1.net1. So if I were to plot v of x1.net1, you can see here that the common source node, when Vn is lower than Vref, the common source node is being controlled by the non-inverting input transistor M1, and so the input, or the common source node, is going up with the input. But then when the input exceeds the Vref node, the common source is controlled by M2, and it levels off. So you can actually see here something that's a little bit uncomfortable, and that is for Vref of 0.75, which is not even halfway up the power supply range. The common source node is already topping out here at almost 1.7 volts, maybe 1.68 volts. And if it takes 100 millivolts to saturate the PMOS bias transistor, that means that my allowable common mode input range is probably only up to about 0.8 volts, or maybe 0.85 volts or something like that. And so that's a little uncomfortable, because that suggests that our common mode input range is less than half of the power supply voltage with a PMOS diff pair. And so we'll have to think about kind of what the implications of that might be. But so we can do this, and we can also then write out the data in the same way that we did from the interactive interpreter just a minute ago. We could have put those commands down here, the WR data, the set WR underscore vec names, set underscore W, or set WR underscore single sweep, or whatever, and then the right WR data command to write out the data that we want into a text file. So that could all be put here in place of the plot command if we didn't want to plot the data in Ngspice, but we just wanted to export the data directly. Okay, so I also wanted to show you one other thing which will become interesting and useful in other contexts. So we have 2 different ways of running this in this particular type of analysis, where we can do the nested DC sweep using by specifying two different sources here to sweep. This one is the one that's swept in the inner loop, and then this one is the one that's swept in the outer loop. But there's another way we can actually do this with a control block, which I want to go over here, and it's kind of interesting for a different reason. And so let me take this out. And we can actually write control structures like loops and things like that in this little control script. And so we're going to define a vector of values that we're going to use in our for vref, and that is going to be using a command called compose vref, and we're going to say start equals 0.25, stop equals 0.75, step equals 0.25. And so this is a linearly spaced vector starting at 0.25, ending at 0.75 with a 0.25 volt increment. There are other possibilities. You can do logarithmically interpolated vectors, you can do a list of values and things like that. But what we're going to do is we're then going to do a loop, which is a for each loop. For each val, and then this is a little bit weird, but it's $ampersand vref. This will basically insert the vector of replace this instance of vref with the list of values as a string. So the scripting language that Ngspice knows is apparently based on the C shell scripting language from Unix, which was apparently all in vogue at Berkeley when Spice 3 was being developed, and so that was kind of the scripting language that they had in their mind as a template for the basis of this. So it's a little bit weird. And I think I'm doing this correctly, but then we want to do alter vref with the value of val. And so what this is going to do is this is going to actually run 3 different DC sweeps, assuming I've remembered the syntax correctly. There's a good chance that I haven't remembered the syntax correctly because I'm kind of new at this too. But so for each is kind of like it's a for loop, and it basically takes the successive values in the list that we provide here and it puts them into the variable val. And then the alter command basically takes some device, which in this case is going to be our vref voltage source, and it changes the value of the vref voltage source to the value, the numerical value that's val variable expands into. And then it does a DC sweep, in this case just a single DC sweep, where Vn is swept from 0 to 1.8 in 1 millivolt increments, and then it runs the analysis, and then it goes back up and it does the next value of val. So there's going to be 3 separate DC sweeps that are done, and we'll drop into the interactive interpreter and plot and write the data out from there. But we could also put what I'm about to do in the interactive interpreter in here. Just let me flip back over to the manual and verify that my memory of the for each variable, and then a list of values, which can be a vector if we use that funny $ampersand notation. Okay, so if this turns out to be something you want to do, chapter 17 of the Ngspice manual is something you'd probably like to spend a little bit of time becoming familiar with. Okay, so let's go back over here and let's say OK. And now let us drop into simulator. Okay, so it's done a sequence of analyses. Here. And you can see each one of them has 1,801 points in it. Okay. If I do the set plot command, you can see that there are 3 different plots here. So a plot is a group of vectors that result from a simulation run. And so it names the simulation runs by the type of analysis and then a number. And so the first run, when vref had the value of 0.25, is stored in plot DC1. The second one is DC2. The third one is DC3. And the current plot is indicated here as DC3. And so if I were to plot V of V out, V of V in, and V of V ref, I would get the result of the third plot only. But I can, if I want to, set plot new to make a new plot. And so now I have the current plot is unknown 3 with a title anonymous. And so if I like, I can, I think, set cur plot title, or I think it's cur plot title, TCs. No, that wasn't it. Set. Cur plot name. That's it. Cur plot name. So these are predefined variables that have certain meanings. So cur plot name would be the way that I would change the name. Well, and again, it's cur plot title. No. All right. Well, let's do the plot anyway. So plot. If I want to plot the V out from plot DC1, I reference that with a dot notation. So DC1 dot V of V out. And let's plot all 3. DC2 dot V of V out. DC3 dot V of V out. And now you can see that I've combined the 3 different voltage transfer curves on a single plot. Okay, so you can do that. And you can also use this mechanism in the WR data command to write out vectors to a file that come from different analyses. So for instance, if we do set WR single sweep, set WR vec names, and we do WR data, and the file name we can give this cmdifamp etc.txt, and now if we give it dc1 dot v of v out, dc2 dot v of v out, and dc3 dot v of v out, and then we flip over to here and look at this, we can see now we have, I must not have gotten the single sweep correct, but anyway, so here we have columns for each of the 3 vectors, and if we go down, there will only be 1,800 lines. And so it might be nicer to have the data in this sort of format for bringing into a different program, just because you don't have to then slice out the middle 1,801 data points and then the last third into separate vectors from the first 1,801 using slicing operations. That could get rather tedious. So with this, we could actually bring each separate column into a different vector. We can again read this into LibreOffice Calc and make it into a CSV file pretty easily. And so there you have it. We can do a variety of different things. So this structure may not be the best idea for a nested DC sweep, because that's fairly easy to do using this mechanism or using the other mechanism, provided you don't mind sort of slicing out the different pieces of the resulting concatenated output into separate curves or whatever. But when we get to doing things like varying parameters, we can also use this alter command, and there's an alter param command, which basically allows us to alter any sort of parameters, whether they're like resistor values or things that we define in terms of parameters inside of like transistor models or whatever. We could do Monte Carlo analysis with this. We can do parameter sweeps with this mechanism. So this is how you would do something similar to a dot step analysis in Xspice. So it's a little more tedious, obviously, than doing the dot step analysis in Xspice, but this turns out to be, I think, more flexible in the end of the day, or at the end of the day. Anyway, so that's it for this. Hopefully it's helpful. If you have questions, let me know. Thanks for watching.